Hello everyone, today I'll be discussing evolving spiky neural networks for autonomous vehicle control and mixed autonomy traffic systems. Some background first. Autonomous vehicles, of course, have been shown to have many potential benefits, such as decreased travel times, lowered energy consumption, and one of the biggest things is they can eliminate human error, which is a prime reason that accidents happen today on roads. However, there's some clear drawbacks as well of AVs, such as there are massive, highly engineered systems that have a bunch of failure points. So technological complexity is an issue. Also, there's large public distrust with AVs because people are not comfortable handing their life over to a machine that they don't really know how it thinks, so to say. As a result, there will not be a transition overnight between human drivers and autonomous vehicles. There are few AVs now amongst millions of humans drivers, and that number is projected to increase, however, that ratio. And so the AVs must work with the human behaviors that are both predictable and erroneous. So this leads to the big questions. How do AVs optimally deal with having a few other AVs on the road, but also having a lot of human drivers on the road as well? And this has led to a lot of research, and a lot of recent research has used deep reinforcement learning to train artificial neural networks to solve this problem. So this problem, which is known as a mixed autonomy traffic system, that is having human drivers and autonomous vehicles on the same roads, and trying to maximize the traffic flow in these road systems. So that way you minimize travel times and minimize traffic congestion and start-stop waves and all of that. So this really started with this bottom left work that really started this deep reinforcement learning for AV control and these closed networks of mixed autonomy traffic. And what they showed is with a single autonomous vehicle, it could stabilize the entire network, traffic network, and even perform and more optimally and maximize traffic flow more optimally than existing traditional control techniques with their artificial neural networks. And these other works here really built off of this original work. And after a while, this framework on the top right was even created called Flow that's built to do just this. That is mixed autonomy traffic optimization using deep reinforcement learning. These works all use ANNs, however. My work uses spiky neural networks. And spiky neural networks, they are neuromorphic neural networks. That is, they're inspired by the biological human brain. They are networks of neurons and synapses. That's all they are. They perform processing based on neuronal fire times. So time matters, unlike with artificial neural networks that just use neuronal fire rates, essentially. When run on neuromorphic hardware, these networks have co-located processing and memory, which can potentially eliminate the von Neumann bottleneck. They're massively parallel, they're low size, weight, and power, and they can be extremely fast. This should make spiky neural networks ideal for a real-time embedded system like a vehicle. The methodology for the experiments in this paper, and the study in this paper. I've started out by creating these three different road networks. These are the same road networks that are created in the Sumo traffic simulator. They're the same ones as this aforementioned paper in the bottom left here. You see this similar ring network here. They're the same ones. However, I cannot find the files and resources to recreate them perfectly, which I wanted to do initially. As a result, I created my own, and as you can see, they're definitely dissimilar in that they have these corners. These are octagons instead of well-rounded rings. And the reason they have these corners of these octagons is that these corners cause the vehicles to slow down around the corners. And whenever the vehicles slow down, they really accentuate these start-stop waves and traffic congestion that are inherent to these closed systems anyway, even without the corners. And that allows more room for optimization over just the imperfect human drivers down the line. So talking about the human drivers in this Sumo simulation, the Sumo cross car following model was used to simulate human driving behaviors. And that will basically cause cars to accelerate at a set rate until they're behind another car. And then when they're behind another car, they'll try to keep a certain headway such that if the leading car suddenly brakes, they have enough headway to where they can brake as well and not have any sort of rear end collision with that leading car. Also, there's maximum speed rules in Sumo that look at speed limit and limiting speed due to an upcoming intersection or turn as well. Um, What's really notable about this slide, though, is that the parameters for all of these things were set such that I wanted to mimic very imperfect human drivers that like tailgate close to cars in front of one another and slow down quite a bit around corners, things that really do obstruct traffic flow and cause the start-stop waves and traffic congestion that I mentioned. Um, so that way there's plenty of room for improvement with the trained spiking neural networks. Moving on to the AV models in Sumo. Yes, the spiking neural networks control the yes, the spiking neural networks control the autonomous vehicles in this work. However, they only partially control the AVs. And the reason for this is primarily safety. This was done on purpose. I do not want the unpredictable neural networks to have full control over the autonomous vehicles. I wanted traditional models like the Krauss car following control model to really enforce safety constraints on the spiking neural network. However, the spiking neural network does get to decide, assuming that's safe, when to brake or when to accelerate. So here's the application I wrote for this project. It uses the TinLab neuromorphic framework, and that's used for spiking neural network simulation, neuronal encoding and decoding. It's used for integration with the evolutionary algorithm I'll get to in a bit, and it's used, for example, for a swarm application interface that will automatically instantiate a spiking neural network for each autonomous vehicle agent, the same spiking neural network that is, and then use that spiking neural network on all of these different agents for decision making. This application was written in C++ using libsumo. And that was done over Python for speed purposes because a lot of training went into this project. A nice part about this application is it supports any Sumo road network. So you can create a new Sumo network and integrate it in with this application very easily. You just essentially give it the directory of the Sumo network, and it needs to have a few routes defined that are expected. The observations for this application are simply for each AV, it has a LiDAR on the front of the AV and a LiDAR on the back, distance sensors. So that means the observation is going to consist of two distance values from 0 to some set max distance value. And that will be an observation for each AV, are those two distance values. The action space is quite simple. It's binary and discrete. You'll either speed up by a certain amount or slow down by a certain amount based off of what output neuron wins in the spiking neural network. So training the spiking neural networks, it's done using the evolutionary optimization for neuromorphic systems, or EONs. And that the way it works, here's the algorithm, is well, actually first, EONs can evolve both SNN structure as well as the parameters in the SNN. And now here's how it works. It starts by generating randomly a population of SNNs. It then evaluates them using a metric I'll talk about in a second, and then ranks them. And then from the ranking, it selects some of the networks, generally the better performing ones, and then it will use those to reproduce the child population. And from there, it rinse and repeats, and each of these evaluate, select, and reproduce cycles is called an epoch. And then here's the score it uses for evaluation and ranking. The score is basically just the traffic flow, like the average speed of any vehicle inside of the road network, and summed across all the different simulation time steps that the Sumo that this application is run for. And so now next, this slide represents all the different ways that data can be encoded from observations into neuronal SNN inputs. But for the sake of time, I'm going to skip over this. So the different experiments. First experiment varies the different observation encoding methods that I just showed on the last slide. The second experiment varies the road network that I showed a few slides ago, and also the AV penetration rate, so the ratio of AVs to human drivers. And then the last experiment, third experiment, varies how much the action values that result from SNN decisions speed up the vehicle by or slow down the vehicle by each time step. For each row of all these tables, there are dozens of EONs training runs that are being done. Each independent EONs training run is 150 epochs of the algorithm that I showed earlier, and so that leads to a lot of training. All of this training took months in CPU time, and in real time, how long it took after parallelization on the Isaac cluster, it took nearly a few weeks to complete all of this training because there's so many training runs done for every single one of these rows. So here are the results of all that training. So experiment one, varying the observation encoding methods. The two plot on the left shows the testing fitness values of the best networks that result from the aforementioned EONS training runs, and they're spread out based off of which spike encoding or observation encoding method that was used for that SNN. And you'll see from the Tukey plot that all of the mean fitness values here are extremely similar, and median values are extremely similar, and so on and so forth. And so a two-sample t-test was done to basically show that every single one of these, when they're compared with one another, all of these fitness value samples, when they're compared with one another, are extremely similar. And the performance of these encoders are very insignificant, which is unfortunate. I hoped one of these encoding methods would prove to be better than others. But on the right, here's a spiking neural network. It just has 12 neurons and 19 synapses. It shows how lightweight these SNNs really are. Experiment 2 results, varying the road networks and the AV penetration rates. You'll see the Tukey plots on the left looks a lot like the last Tukey plot we looked at, and you'll see that as you increase the AV penetration rate, the testing fitness values of the best SNNs increase. That makes sense because you're reducing those imperfect human drivers that I mentioned before and increasing the number of autonomous vehicles instead. So as a result, overall traffic flow improves, as can be visualized here. Now looking at the delta speed values, the action values, so how much it brakes or accelerates each decision. On the Tukey plot on the right, same sort of Tukey plot we've been looking at, as the delta speeds increase, so do best network testing fitness values. However, it plateaus. So there really is a sweet spot for the best delta speed that you can have. Finally, assessing SNN performance. What was done in this top right table is that 0% AV penetration, that is human drivers only, were tested on each of the rows with all the different testing seeds that were used for all other post-training testing for all the SNNs. And here are the resulting fitness values that occurred. And so what you'll notice is on the bottom right here is the Tukey plot we looked at for experiment 2, is that for every single road network, all of the testing fitness values that SNNs in the Tukey plot are all higher than the human-only testing fitness values. This means that SNNs consistently beat human model performance, which is good. That's the whole reason the training was done in the first place, is to improve the traffic flow. But however, when you qualitatively look at this, you'll just see that the SNNs are far from optimal. So on the left here, this figure 8 is a reinforcement learning approach versus the SNN approach. And you'll see on the left, there's no stopping intersections, while the right has a lot of stopping intersections. In conclusion, successfully trained these spiking neural networks with EONs to improve traffic flow and to create these very small, lightweight SNNs using this app that I created with the TinLab framework. I ran some experiments varying some different parameters on it to draw a few conclusions. And so I was able to do this successfully and improve traffic flow over human drivers. However, the trained SNNs were qualitatively shown to be far from optimal and not able to fully stabilize the systems like the reinforcement learning agents were. So for future work, I think a hyperparameter optimization with EONs would help a lot here with improving fitness. I think I could tweak the fitness function to incentivize braking for maximizing long-term rewards. I think that would help. And I think that adding leading and following vehicle speed values to observations instead of just having distances would be useful as well. I also think that adding more delta speeds to action spaces would give more granular control that could improve performance. But most importantly, I think extensive performance comparison with existing ANN reinforcement learning work is imperative to really compare the SNN work that I've done here with the existing RL ANN work that's already been done. And the only reason I didn't do that was really for the sake of time for this. Building the app and doing weeks of EONS experiments meant that I did not have time for extensive performance comparison with existing work because I'd have to replicate that existing work as well. Here are my references. Thank you very much. If you have any questions, feel free to email me at this email address.